Hello, happy day everyone. This is Horekoya Olusegun, Physics Mathematics Fundamental on YouTube. Please, before we go into today's topic, as usual, do not forget to like, share, subscribe. Click on the notification button to have more of my video. For partnership, please, this is my mobile line 0814136457 and for sponsorship so that this video can reach as many clients as possible all over the world. My OPay account number is 814136457. I will appreciate any level of partnership. Thank you. Today we are taking a topic in mathematics, and that topic is under calculus. And this particular topic is how to find instantaneous rate of change. That is derivative at a given point. I mean, from the given from average rate of change. How do we do that? Now, let's say we are given this expression. Let's say we are given y is equal to x squared. The question says find the y dx at point x is equal to let's say 4. At point x is equal to 4. So okay, at point x equal to 4 in the interval 2 4 2 5 on x axis. Now, what this one is actually saying is this. Let me give arbitrary diagram of this problem. Y is equal to f of x against x. So we want to find the instantaneous rate of change when x is equal to 4. That means to find the y dx is equal to 4 within this particular interval of 2 and 5. Now, what we need to do in this case is this. Let us first use the fundamental formula in deriving what our answer will be first. I did that derivation of that fundamental derivative in my last YouTube video. Now, if you are given y is equal to x raised to power 2, the y dx will give you 2x. So at point 4, the y dx when x is equal to 4 will be 2 times 4, which is equal to 8. So that means the y dx when x is equal to 4 for this function f of x is equal to y, which is x squared. The y dx will give us 8 when x is 4. So what I'm going to do now is to use the idea of average rate of change to have the approximate value at when x is equal to 4, what the value of the y dx will be. So what I'm going to do is this. I'm going to reconstruct this. I have the value of my x to be 4 here on the x axis. So what I'm going to do is to get certain values that are close to this 4 within these limits that we have been given. We are given this limit 2 and 5. But I'm going to get a point that is close to 4 here. So the two intervals that I'm going to use will be something like 4.0001 to this side of 4, because I'm getting certain points that are close to 4, and to this other side of 4 that is a bit less than 4, I can have something like let's say 3.9991212349999. So you can see now I will use this one as my x1, as my x2 in calculating the average rate of change, so that I would see what my answer will be for the instantaneous rate of change when the value of x is equal to 4. So what I'm going to do now is this. You know that the average rate of change, which is delta y divided by delta x, is given as y2 minus y1 all over x2 minus x1. This one is the average rate of change. Average rate of change. Don't forget this particular formula. So, and then the meaning of what I've written down there, we can rewrite it equally as f of x2 minus f of x1. F of x2 is this y2 minus f of x1 is this y1 divided by x2 minus x1. Now, since our y is equal to x squared, that means f of x is equal to x squared. Now, my x2 here is this particular function. So I will put when my x is 4.00, I put it here for the x2. So I use this formula now. And then this particular thing that I have here will be, according to this function, the x2 is going to be x squared. I'm going to square it. That is x2 squared minus, for this x1, the function says you square it. That is x1 squared, then divided by x2 minus x1. Now, this particular function that I have here, my x2 is 4.001. So I'm going to write 4.0001. So I'm going to write it as the approximate rate of change. That is limit, approximate rate of change, but using this average rate. Let me write this one as delta y divided by delta x is equal to 4.0001 square minus 3.9999 squared divided by my x2 is 4.0001, take away s1, 3.9999. So now let me create a space here. You see, we need to use calculator to find what this expression will give us. So I will press 4.0001 squared minus 3.9999 squared, then divided by 4.0001 minus 3.9999. So what I have here is actually 8. So the limits as delta x tends to 0 of this average rate of change, delta y all over delta x, is equal to 8. It depends on the option that you pick here. Just make sure that whatever you are picking to the right of this particular form we are looking for, and to the left of this same particular form we are looking for, is approximately equal to 4 in each case. Take whatever you have inside the expression for the average rate of change. The limits we are going to have will be almost equal to or exactly equal to the instantaneous rate of change. I believe that you have been able to appreciate how you can use the idea of average rate of change to determine instantaneous rate of change at a given point on the axis for the independent variable. Now, as a reminder, I want you to recall something, please. When your derivative, the y, the x, is equal to 0, when you have it is equal to 0, that means the instantaneous rate of change of dependent variable is 0. Now, That means the quantity is neither increasing nor decreasing. I'm talking about if you put this thing on diagram like this, look at it. As you are moving like this, the value of, as you are moving along this curve, if you are looking at the y-axis, the value will be increasing. As you are looking at the x-axis, the value too will be increasing until you get to this particular point at which we have the y, the x is equal to 0. The value will not increase nor decrease. But as you are moving after this particular point here, this particular point is known as turning point. Turning point. As you are moving, if you are looking at the value of the y-axis, it will be decreasing, while that of x will be decreasing, will be increasing. So in a nutshell, when you have the y, the x to be greater than 0, we have what is called increasing function. Increasing function, which is also known as growth. Now, when you have your dy, dx less than 0, that is negative, we have what is called decreasing function. And this decreasing function is also known as a decaying function. Decaying function. So here, the value of my dy x will be positive because the value keep on increasing. Here is equal to 0. Here the value is decreasing. So here is negative. This particular side is for the decaying, and this particular side is for the growth. Thank you so much. I am quite appreciative for the fact that you have been able to comprehend also the idea of what is increasing and decreasing function is, and what is growth and decaying is, especially in scientific communication. Thank you so much for having you around. Have a nice day. Bye.